Hello everyone, I'm Adelia Agustin with my last student number is 046.
My name is Derisca Fladinda and my student number is 0601128227050.
Hello everyone, my name is Fatimah Aqilah with the lesson number 049.
Hi, my name is Meilani Amelia and my live student number is 047.
Hello everyone, my name is Hilda Pinasti with my last student number 051.
Hello everyone, my name is Windah Salsabilah P and my last student number is 048.
Hello everyone, I'm Adelia Agustin with my last student number is 046. Today, we are going to present about one-way Anova. So, let me begin by explaining what Anova is. Anova stands for Analysis of Variance. One-way Anova is a statistical method used to compare the means of three or more populations. It helps us determine whether there are any statistically significant differences among the means of different groups. In this method, we use key term called a factor. A factor in Anova refers to the cause of variation in the data. When we consider only one factor, it is called a one-way Anova. Within each factor, we have what we call levels. These are the different categories of that factor. The simplest type of ANOVA is called a completely randomized one-way ANOVA. It involves selecting observation independently and randomly for each level of one factor. This means that each observation is chosen randomly and doesn't depend on others. To correctly use one-way ANOVA, there are three important conditions that must be met. First, the population of interest must be normally distributed. That means the data should form a bell-shaped curve when plotted. Second, the samples from each population must be independent of one another. This means that the data is one group doesn't affect the data in another. Third, each population must have equal variance. We also call this the assumption of homogeneity of variances. In simple words, the spread or variability of data in each group should be about the same. When conducting a one-way ANOVA, we begin with two hypotheses. First, the null hypothesis, written as H0 or H0. It says all populations means are equal. For example, mu1 equals mu2 equals mu3. Mu refers to the average or mean of each group. Second, the alternative hypothesis says not all the means are equal. So, at least one of the group means is different from the others. If the test result leads us to reject the null hypothesis, it means that there is a difference between group means. However, we need to remember that ANOVA doesn't tell us which group is different. It only tells us that a difference exists. For that, we will need to do a follow-up test. Alright, that's all for me. The next material will be explained by my friend. Thank you.
My name is Derisca Fladinda and my student number is 0601128227050. Now, I will continue explaining the material. It is about partitioning the sum of squares in ANOVA. The hypothesis test for ANOVA compares two types of variations from the samples. The total variation in the data from the samples can be divided, or as statisticians like to say, partition, into two parts. The first one is sum of squares within or SSW, and the second one is sum of squares between or SSB. Now, let's talk about sum of squares within or SSW first. So, SSW shows how much the data varies inside each group. It's also called the error sum of squares or SSE because it shows variation we can't explain by group differences. This is the formula to calculate SSW, where K is the number of groups or samples, and sub I is the number of data points in group I, and S sub I squared is the variance of group I. Now, let's see the example of sum of squares within, or SSW. Here, we have three groups. Each group has 6 observations. Their variances are 1.01, 1.70, and 0.96. We can add these values into the SSW formula, and the result is 18.35. This shows the variation within each group. Let's move on to the second one. It is sum of squares between, or SSB. SSB shows how much the group averages or means are different from the overall average. So basically, it tells us how much the groups differ from each other. If the group averages are very different, the SSB will be big or large. If the group averages are similar, the SSB will be small. Here is the formula to calculate SSB, or sum of squares between, where K is the number of groups and sub I is the number of observations in group I, X bar sub I is the mean of group I, and X double bar is the grand mean, or the average of all the observations. Now, let's see the example of SSB. Here we have three groups with means 9.12, 10.92, and 9.48. To find the grand mean, we use this formula. Then we got 9.83 as the grand mean. After that, we plug the value into the SSB formula, and the result is 10.86. This shows how much the group's means differ from the grand mean. Finally, the total variation of all the observation is known as the total sum of squares, or SST. It can be found using this formula. But instead of calculating it manually, we can just add the values we already found. And the result is 29.21. This is the total variation in the entire dataset. To find the variance of all 18 observations, we use this formula. This gives us overall variance for all the data combined.
Hello everyone, my name is Fatimah Aqilah with lesson number 049. Today, I'm going to explore about F statistics, but before we move on, I would like to ask you one question. If we are going to find out about do different teaching methods really make a difference in student performance, how are you going to answer that? Well, no worries. To answer that, we will use a very simple statistical test called the F test. That's what I'm going to explain to you about. Hopefully, with the case study, you will get to it much better. Alright, let's say we have two classes. Class A uses traditional one, while the class B uses interactive method. So as you can see on the screen, here are their scores. Remember, what is our goal? Our goal is to find out whether the difference in scores just random or does the teaching method actually matter. Okay? If both methods are the same, we'd expect that the scores to mix randomly. But if one method is better, the class using it will have a higher scores more consistently. Okay, now we will measure how different the averages are between classes, or we call it mean square between, versus how much scores jump around within each class, or mean square within. Okay, now let's get it answered. First, you have to find out the class averages first. For the class A and the class B, here I got the numbers. It looks like a big difference, okay? But let's see. And then we have to find out the mean square between, which is to, measures difference between A and B, as you can see the formula on the screen. And this is what I found, 72.9. And we gotta find the mean square within as well. And here is the result that we got for it. You can see on the screen. And now the final step. Let's insert the formula, which is f equal mean square between divided by mean square within. And we got this, 16. But what does that mean? We compare our result to F distribution table. So we set the alpha, which means, 0.05, which means we are okay with the 5% being wrong. And we need to revert to an F distribution table, and here's how you find it. So the F distribution table gives us critical values based on three factors. First, the alpha. In our case, we set the alpha is 0.05. And then the degrees of freedom between groups, and this is the number of groups minus 1. And we got it 1. And then we have got to find out the degrees of freedom within group, and this is the total number of observations minus the number of groups. Okay, since there are 10 data points, 5 from each class, we got 10 minus 2 is 8. Okay, now we are going to use the table. We go to the F distribution table and find the critical value for the F1 equal 1, the F2 equal 8 at 0.05 significance level. And when we look it up in the table, we find that the critical value is this, 5.31. Okay, since the result that we got, 16, is higher than 5, that means the difference is real, not a random one. And not only that, we can say that the teaching method does actually matter in this case. Students in the interactive class perform better, and the difference was statistically significant. Okay, that's all about the F statistic. Hope you learned from me. Thank you.
Hi, my name is Meilani Amelia and my live student number is 047. So you've heard the explanation about the introduction of one-way ANOVA, the partitioning of the sum of squares, and also determining the calculated F statistic and also the critical F statistic. Now, I'm going to explain about how to use Excel to perform one-way ANOVA. So without further ado, let's move to the tutorial. All right. So first step is start by placing the data in columns A, B, and C in a blank sheet. So we want to compare the 3 or more populations here. So that's why we have 3 data here, group 1, group 2, and group 3. All right. Now go to the tools menu and select data analysis. So in my Excel, data analysis is in here in the data menu. So we click data menu and also click the data analysis here. Okay, so choose ANOVA single factor. Also click OK. All right, now we have input range here. So in this box, input all the data here. So we block the data here with the labels. And then this checked labels in first row. And also the alpha is 0.05. And also for the output range, you choose where to put your data. So for example, I want to put the result here. And then you click OK. All right, now we have the result. We have 2 tables here. There's the summary table, and also there's the ANOVA table. And we focus on the p-value here. That's highlighted. All right. So you notice that the p-value is 0.0305. So for this test, the p-value is lower than 0.05, which means that the null hypothesis is rejected and the alternative hypothesis is accepted. It means that not all the population means are equal here.
Okay, now we've got the result of the one-way ANOVA. Now I'm gonna write the hypothesis here, and I'm gonna read it.
All right, so I've already copied the two tables here, the ANOVA tables here, and then this is how the hypothesis looked like. So for the null hypothesis, all the population means are equal, and for the alternative hypothesis, not all means are equal. So the result of the ANOVA single factor test show that the obtained p-value is 0.0305, and since the obtained p-value is lower than 0.05, null hypothesis is rejected and the alternative hypothesis is accepted. It means that not all the population means are equal.
Alright, I think that's all from me. So for more detailed display of one-way ANOVA test, it will be better if we use SPSS to display the data, which will be explained by the next presenter.
Hello everyone, my name is Hilda Pinasti with my student number 051. So, in this video, I will explain about pairwise comparison using the Shape A test. Once we have rejected the null hypothesis using ANOVA, the next step is to find out which specific group means are different. To do this, we use a pairwise comparison method. Pairwise comparison helps us compare the means of each group with one another to identify significant differences. One popular method for pairwise comparison is Shape A method. It's known as a conservative method, meaning it's very careful and helps us avoid wrongly saying there's a difference when there is not. For example, if we have three groups, we will compare group 1 with group 2, group 1 with group 3, and group 2 with group 3. This is called pairwise comparison, where we compare the mean x bar of the groups at a time. Now let's take a look at the formula. This is the formula to calculate Shape A's f-value or f sub s, where x bar A and x bar B are the means of group A and group B. SSW is the sum of squares within groups, which measures the variation within each group. NA and NB are the sample size of group A and B. And sum of n sub I minus 1 is the total degrees of freedom within groups sum across all groups. Next, we compare it with the critical value with this formula. This is called Shape A's critical f-value, where k is the number of groups. F at alpha with degrees of freedom k minus 1 and n minus k is the critical value from the F distribution table, depending on our significance level alpha and degrees of freedom. For example, the alpha is 0.05. The number of group is 3. Degrees of freedom are 2 and 15. So, from the F distribution table at alpha equals 0.05 with degrees of freedom 2 and 15, the F value is 3.682. Then, S sub SC equals 3 minus 1 times 3.682, which equal 7.364. So the Shape A's critical value is 7.364. Now that we have calculated both F sub S and F sub SC, let's use them to make decisions about the group comparisons. So if F sub S greater than F sub SC, we conclude that there is a significant difference between the two groups. If F sub S less than F sub SC, we conclude that there is no significant difference. Let's look at the table. First, x1 and x2 have an F sub S or F value of 8.048. Since this is greater than 7.364, we conclude that there is a significant difference between group 1 and group 2. Next, x1 and x2 have an f sub s or f value of 0.323, which is less than 7.364. So no significant difference is found between those groups. Finally, x2 and x3 have an f sub s or f value of 5.142, which is also below the critical value. So again, no significant difference. According to the results, the only statistically significant difference is between group 1 and group 2. I think that's all from me. Thank you.
Hello everyone, my name is Windah Salsabilah P and my last student number is 048. And welcome to my presentation about using SPSS to perform one-way ANOVA. Some of my friends have already presented related on topic. I will continue to operate one-way ANOVA. So, I'll guide you through the step using SPSS to perform one-way ANOVA.
Alright, so before that we have mass variable view. In variable view, number 1 is method and number 2 is score. In method, decimal is null. Label you can change to teaching method name. Value, you click. Value is 1, label in method A, and you click add, and so on until 3 is method C. Click OK. And columns 10 and measure you change to nominal. And for the score, decimal is 1, label test score, value none, column 10, measure is scale. And we jump to data view. In data view, in method column, this column shows that number 1, number 2, number 3, and again and again. The numbers mean different groups or method. 1 is method A, 2 is method B, 3 is method C. Scar column. This column shows numbers like 10.2, 8.5, 8.4, 10.5, and so on. These numbers are the result scores, and we can continue how to perform one-way ANOVA. We click Analyze. We click Compare Means. We click one-way ANOVA. Dependent list, you put test score and factor and teaching method. We click post hoc. We click LSD, Shefish, and continue. And then options, descriptive, homogeneity of variance test, and means plot. We click continue, and then click OK. And so we get data like this. And now we get the result or output, like descriptive, test of homogeneity of variance, ANOVA, multiple comparison, post hoc test, homogeneous subset, test score, and means plot. And now here is some explanation of the result we got.
H naught mu1 equals mu2 equals mu3. All the three means are equal. H1, not all mu's are equal. Not all the three means are equal. The results of one-way ANOVA show that the F obtained equals 4.439 and the P value equals 0.031. Since the P value 0.031 is lower than 0.05, H naught is rejected and H1 is accepted. This means that not all the three means are equal. The results of Cepheids test show that there is a significant difference between method A and method B, with a p-value of 0.041, which is less than 0.05. There is no significant difference between method A and method C, with a p-value of 0.849, which is greater than 0.05. There is also no significant difference between method B and method C, with a p-value of 0.114, which is also greater than 0.05. The mean of group A, written as x bar sub A, equals 9.117. The mean of group B, x bar sub B, equals 10.917. Therefore, method B is significantly better than method A. So that video group presentation from our group. Thank you for watching and pay attention. Wassalamualaikum warahmatullahi wabarakatuh.